Hi, this is Alex Pault with Open Systems Media and Embedded Computing Design, and I'm actually here in Silicon Valley at the pre-switch facility with Derek Kroes. He's the Vice President of Engineering. Hi, Derek.
Hi.
And James Hamond. He's the CTO. Hi, James.
G'day.
Well, you know, James, I was at the show recently, APEC, the Applied Power Electronics Conference, and in fact bumped into your CEO, Bruce Renard, and who invited me here, and so I managed to talk you and him and Derek into putting together something and actually taking apart some of the work you were actually trying to accomplish, just so you could give us an opportunity to explain to the audience exactly what this all means, because there's a lot of rumor, actually, because people aren't quite understanding, because unless you hear the whole thing, it's hard to pick it all up, right?
Absolutely. We're glad you dropped by, and we certainly did our best to throw something together to give you the best demonstration of our capabilities in the short time we had. So hopefully this is exciting for everyone.
Well, I think it is going to be, well, everybody knows I love power, right? So I think we'll be able to make it. And Derek, feel free at any point to jump in. I don't want you to just think that, you know... Okay, excellent.
Wonderful. Well, so what we have here is currently a full bridge system that is basically two half bridges that we are driving with an encoder box here that we've developed. Basically, even though our customers will be doing all of this, this is an Arduino-based test platform. The goal is that we reproduce the test setup the way our customers would. And basically, it is a control loop that has a current sensor. It has an encoder on board, PID controller, classic, and then drives the two halves of the bridge to produce some form of modulated waveform. In this instance, it's going to be a sine wave that we're running at 50 kilohertz. Now, we have done a sweep of frequencies. We've gone from, say, 30 kilohertz all the way up to 100.
The output frequency is much lower, it's 60 hertz, because this is really a solar inverter prototype. But the chopping frequency for the IGBTs is 50 kilohertz.
FSW, yeah, that's correct. So yeah, as you said, so 60 hertz fundamental, just like you would have in the grid. And I think we're looking at a voltage of around 220, but again, it's controllable, as we'll demonstrate in a second. And the idea is that you'll be able to see us moving the currents up and down, and we're able to show you the pre-switch technology varying and adapting over the sine wave. And again, unfortunately, the limitation of the time we had to set up, we haven't got a very fast transient to demonstrate, but you'll get the idea of how the system adapts and must to be stable in the field.
Excellent. So please walk us a little bit through this. Where do we start in the chain?
Okay, so just to give you a quick test setup, and so people know where to look. As we have over here, this is a power board. If we can get a look there, you have IGBT half bridge over here with separate diodes and IGBTs, two IGBTs and two diodes in parallel. Over here is the other bridge. In the middle is our resonant components. So you can see there's very few resonant switching devices, and of course the resonant inductor over here behind our current probe we'll be able to show you up here on our thermal camera as well, so you get a feel for the size. This system here is rated, Derek, help me out, what's the power rating of this one again?
Of 10 kilowatts.
10 kilowatts peak, that's right. We won't be running it at 10 kilowatts today, but it is capable of running up to those currents at 220 volts, which means an RMS current of 50 amps. But today we'll be probably keeping it below 20, again, time of the setup that we had. So as I mentioned, current loop, you can see we've got well, this is Derek's baby here. I'll let you explain what that is.
That's a giant magnetoresistance-based sensor that we're using for the current measurement that feeds back to our control box.
So basically it's a current control loop. So as you can see, there's very few capacitors on board. We have basically some film caps here for decoupling. This card you can see here is one of our earlier pre-drive boards designed for the EconoJewel originally, but we adapted it for this demonstration. So what we're going to do is I'm going to turn the device on with the Arduino box here we call the PDS. I'll turn it on to begin with, and we'll start off with some static currents. You'll see up here on the oscilloscope. The green line is the output current. The magenta, which is channel 3, is the resonant current, and I'll show you that in macro. And the gate drive is the yellow line, trace 1.
It's 350 volts DC.
Excellent.
Okay, and so forgive us for all the ambient noise. We have our power generator, and eventually the cooling system will turn on as well, but hopefully the audio comes out as well. And as I mentioned before, up here is some exciting things where we have that the thermal imaging camera will show us how things tend to warm up. Now, remembering that we don't have any forced airflow, this is a static cool system, so we won't run it indefinitely, but you'll see that it is actually still quite cool at the powers we're going to be generating. All right, so without further ado, I'm going to press the go button. Oh, and I already had it set to current. So as you can see, there's some scrolling right now. I'm just going to zoom in and do a single snapshot so I don't have to have all that scrolling in front of us. So what you can see here is this is the low side gate drive waveform. You can see that when the low side tries to turn on, because there is no load current, we have to soft switch the bridge, and that's to discharge the additional capacitance that we put across the IGBTs to dramatically lower the switching losses. So if I zoom in on this section here, you'll see there's relatively speaking, a negative, what we call the ARCP pulse, and it looks very half-wave sinusoidal. We have IGBTs that are controlled with our system. We're actually able to soft switch pretty much any device with IGBTs with this technology. The beauty of this particular soft switching topology, known as the ARCP, has current that is self-extinguishing, so we don't have to worry about the resonant devices having tail current losses. So you can see a nice resonant pulse here. Just at the magic moment, our system somehow knows how to turn the gate drive on. Now, if I bring in the bridge voltage, you can see that you have a nice sinusoidal with a bit of a lip here. Again, it's not an optimal setup right now, just purely for demonstration purposes. But you can see the device almost picks the minima beautifully. And you're only looking at, I think that's what, peaking back up at about 30 volts, which is a lot better than the full, bearing in mind this is a full differential probe, so we have differential probes on channel 2. You can see that from here to here is actually 700 volts differential. Anyway, you can see because there's no load current, we actually have symmetry. It's soft switching in both directions. When the low side device turns on, we then have the IGBTs, in this instance the diodes, eventually the current stalls, then you have the bridge doing the resonant waveform, and then we can't see it here, but the high side switch will turn on to coincide with that lump there, which is basically the symmetry of this one. So that's a static case. So now, I'm going to turn off a few waveforms so we can see this more clearly. So to start with, we have basically DC current. You can see as I wind this up, I can produce the modulated, the demodulated current waveform of the bridge I'm about to show you. Right now we're at about, I'll wind this up to, let's say 16 amps. I think that's probably a nice level there. Over here we have a power analyzer. If I can bring your attention to this. So the output right now is 2.6 kilowatts. And the system is running an efficiency of 97.62. And remembering these are IGBTs switching at 50 kilohertz. As can be seen over here back on the oscilloscope. Over here, you can see that is showing you the switching frequency of the gate drive, which is of course the FSW. So that's right now running at 50 kilohertz. So I'll increase the power just a little more. Now if you look back over at the efficiency now, you can see we're north of 98% with a poorly calibrated N4L, I should also stress as well. We suspect there's probably a considerable error in this and working against us. It's probably closer to 98.5. But you can see again, IGBTs, 50 kilohertz, and north of 98%. So I'm going to do a single on this. I'm just going to, looking at the thermal imagery right now. Stay out of the way of the camera.
3.6 kilowatts output.
Okay. Right, 3.6 kilowatts. So as I mentioned before, we don't have any airflow on this system, so I won't run it for too much longer. But you can see that the device is the hottest point on that board is 85 degrees, and these are, if you look back down at the circuit board, these are surface mount IGBTs that are being heat sinked through the FR4. This is actually, from a manufacturing point of view, you're getting tremendous power with surface mount devices with incredibly simple manufacturing process. So if I can bring your attention back to the oscilloscope, I'll bring back some waveforms for you here. And unfortunately, our the current probe on the resonant device is starting to saturate. That's a current limitation of the measurement device, but you can see the same resonant pulse as before. Now you'll notice now that the actual duty cycle is much smaller. That's because it's at the peak of the sine wave. If I bring the gate drive back in, you can see it's the crest of the sine wave. So of course you have the minimum modulation index. A bit more on the setup we should mention is the inductance, Derek, on the load.
I believe it's about 500 microhenries with some resistance in series on the order of, what was it, about 12 ohms or 8 ohms? It was 8 ohms, I think. Yeah.
We can work backwards from the math, but the point is that there is the inductance is what's providing the filtering of this scheme. And of course, being 50 kilohertz, even with that inductance and the differential voltage we mentioned is 700 volts, the ripple is tremendously small, which is very good when it comes to if you're using a sand dust or some sort of filter. It's wonderful for lowering system losses. And of course, you would have the ability to lower the inductance in the system to lower cost and meet system requirements. So back to this system here, bring your attention back to this waveform. You can see, if I bring that down there, so again, gate turns off. This is what we call the self-resonant edge. You'll notice that there's no resonant pulse here this time. We call it the self-resonant edge because in a way, it mimics what you would see in your normal DC to DC, LLC, or equivalent converter. All you do is turn the device off, and the current is going in the correct direction such that the capacitance just rises at a nice, gentle VDT that we can control with, of course, the capacitance that we use. So this is effectively the rise time. If we do some quick scanning with our probes,
Which is controlled by the capacitance that we add rather than the turn-off speed of the IGBT.
absolutely. So,
Could you repeat that just to make sure that the mic caught it, because he was a little bit of a distance away?
so as Derek was saying, the VDT is now completely controlled by our added resonant capacitance, which, going back to the device over here, is simple low-cost MPO or COG capacitors in between. You can see the capacitors. It's hot. You have to remind myself. Those capacitors there and there. So very cost-effective. There's no huge amount of capacitance required. Just as with the resonant inductor over here, the resonant inductor in this case I think is an low profile RM8 for up to 10 kilowatts. So a common question we get is, how big is a resonant inductor? Well, it's trivial in fact. So back to this, having the point here, we can see that we have over 400 nanoseconds, we have, let's call it for argument's sake, 630 volts. So that's roughly 160-ish volts. You know, I have to edit this part out. I'm making me do math on a Friday night.
Well, then you skip it over if you like. I mean, don't worry about it.
Anyway, so the point is that the volts per nanosecond are I think it's 1.5 volts per nanosecond. Incredibly low.
Well, they also know that this isn't staged, because otherwise it would be perfect.
Yeah, exactly. Well, that's my genre is rustic. So as we have incredibly low VDT, when the gate drive, the gate resistances on these IGBTs is in the order of I think sub-ohm. So ordinarily that would be a huge problem, because you have to have the right amount of resistance so that you don't have any ringing when you're hard switching, because you end up with a system that starts to oscillate, it jumps around, EMI problems. And in fact, the manufacturers tend to have a very large gate resistor to slow down this VDT we mentioned earlier. That's basically the only way they can control it. But funnily enough, depending on the IGBT, when you turn it off, if it's, say, the style of a Connor Joules, like the larger industrial grade, the gate resistance has almost no impact on the turn off, only the turn on. So they still have limited options, whereas with ours, we affect both.
Okay, now James, how is this solution manifested in hardware for the customer? Okay, you know, what's there? What do I have to buy? Is it a big box, a little box?
Obviously, it depends on the market space and how many phases and all of its requirements. But to give you an example, this is what we're calling our pre-drive 3. This is a 3-phase equivalent of the single phase that we've bridged to full bridge mode over here behind me. So you can see it's still not completely populated, of course, but this device here has all of the components necessary for monitoring bus links, for controlling the ARCPs, and driving all three phases. So if we can, I'm going to reach a bit of hardware behind you.
Sure, sure.
So come back over here.
Actually, then, while I'm here, what is this with the motor behind us?
This is a motor out of a Daimler smart car, electric smart car, and it's a I believe a Bosch, or we believe it is a Bosch permanent magnet motor, and
Could be Continental. They're doing the stuff now as well.
yeah, we're not sure actually. It says Zytec on it, but we are going to use it for testing, and one of the first things we're going to examine is the core and copper losses as we change the frequency from very low, 2 to 5 kilohertz, up to 50 or 100 kilohertz, and at various DC currents. We just want to see if we can measure the losses in the stator and the core as a function of frequency for identical current conditions.
Very cool, Derek. So, James.
So just to finish what my associate was saying, something that the EV industry is coming around to realizing is that while they are designing their motors to run in, say, in Tesla's case, ludicrous mode or plaid mode, I think is the next one, and it's very efficient. Induction motor in particular, it's been designed just right. But if you design a motor for peak power, then you'll have certain inductances and certain parameters that have best performance at those specs. But when you're driving at 5% power like you do on the freeway, you've now got a motor that is suboptimal for those speeds. So you have the choice. You can design it for cruising point, which is companies like CleanWave have done in the past, or you can design it for ludicrous mode. And sadly, if you're going to have cars that can accelerate hard, you actually have to design it for the upper end, otherwise you overheat. So what that means is you have a motor that its primary purpose is for spinning, as we all know. But the problem is the industry using their variable frequency drives with an switching frequency, known as the FSW, they then say, well, we'll also use this motor as a filter. It's actually a really bad filter. It's not designed to be a filter. Like if you actually were using it as a filter, you would not use iron laminates for a start. You would use sand dust or other sort of material because it's far more effective or cost effective and efficient and a lighter weight. So because they've done this compromise, you now have an iron core system that is being used as the filter. Mm-hmm. So
Relatively high frequency.
Well, exactly. For iron laminates, horrendously high frequencies. Even 5 to 10 kilohertz is way too high. So you have this suboptimal filter that's now also your motor. So what we want to demonstrate is, just by changing the FSW, the obvious thing that will happen is the ripple will be proportional to the frequency and the voltage. So keep the voltage steady, adjust the frequency. As in the chart behind Derek over here, you can see two different frequencies. You have 5 kilohertz and what's the one below? 25 kilohertz. So that's a multiplier of just 5. You can see the difference in ripple through the motor.
Very nice. Okay, so now back to this technology, or actually it's the same technology, but this aspect of the technology.
So this is the electronics that drove the motor we just described a second ago. I just want to show the difference in size. So these two boards here sitting on top of the hybrid pack do the job of that board. Now, for full disclosure, of course, we will have some RPGI components on this system as well. So in fact, I probably say let's do that again. No,
You're
right.
in this now.
All right. Well, in that case, I'm going to bring this out. Can you pick that
I'll
up?
hold it here.
Oh, yeah,
Let
if
me
you
hold
hold
this
that.
like this. That'll work.
So this is our coming RPGI that we're designing for north of 200 kilowatts, and now, of course, it hasn't got the 247s, but the trained eye will notice that the pin spacing. This is where we will have our ARCP. In fact, ARCP is up this side. This is the resonant inductor. Obviously, it's larger than the board we showed you before because it's designed for 200 amps or so, that sort of vicinity. Over here, you have triple sets of high side and low side switches times 3 phases. So this board here we can verify and demonstrate either silicon carbide of various voltages, IGBTs of various voltages, and of course varying frequencies, all controlled by this card sitting on top.
Well, that's excellent. Now, James, you had mentioned wide bandgap semiconductors, but the kind of size reduction you're showing me is normally what wide bandgap companies do when they say, hey, move to wide bandgap. So are you more of an enabler for silicon, or are you more an enabler for wide bandgap? Where exactly do you see your support fall in those two areas? I realize you probably work for both.
Absolutely. So I guess the short answer is that we are able, as we demonstrated, to make IGBTs switch faster than wide bandgap in the same conditions. So we're getting similar switching losses, if in fact better, using our technology. Now, of course, as your viewers will know, we can of course add our technology to other switches as well. In fact, strictly speaking, we can soft switch relays and thyristors. I don't know why you would, but we could. So yes, we basically amplify whatever you have. That's what it comes down to. Excellent.
So now, James, they probably know, but why don't you just tell us the URL again so we have a record?
Our website is it's www.pre-switch.com.
Excellent. So now, do you have any last words for our audience before I let you go? This is running a little long, but I think that they would appreciate the fact that we went granular on this and gave them some real information.
There's something important I haven't shown you back over here on the screen, if I may.
So cross over behind me, then we'll go over here, and you show me real quick, and yeah, we'll be fine.
Okay, I mentioned early on that the system adapts in obviously over the from cycle to cycle, as we call it. So what's important to notice here is, and again, it's a sine wave, so we don't have massive changes. Obviously the green fundamental, the output current waveform has very small steps in it, but you can see that, as if by magic, these current waveforms here. In fact, you can see in the macro view, you can see the resonant pulse changing with the load current, and that's basically the essence of what's different about our system to what was tried in the previous decades. It's all about being adaptive and being predictive. And the last point I want to leave the viewers with on this one is that in the past, and those who know anything about the field know that ARCP was developed in the 80s, and it was hailed as the savior, and then disappeared in the late 90s when everyone decided that they just wait for better switches. Now, as we know now, you can have a better switch, but you still can't use it to its full potential, because then you have things like overshoot, you have DVDT problems with motors that cause bearing currents, EMI issues, etc. So while even the wide bandgap devices promise, hundreds of kilohertz, they're still sub 100 kilohertz in most applications, sometimes sub 40. In fact, I think it's probably common knowledge now that even the Model 3, which uses silicon carbide, is switching at just south of 10 kilohertz. So they're spending the sort of capital requirements on just the parts, forgetting the engineering costs, etc., just to go to silicon carbide. And I have under good authority that's to save 1% of losses in the inverter, a whole 1%. So,
well, it does add up.
It does. Anyway, so to round off the important point here is, in the past, what people tried to do was say, I know the current, I know the volts, I'll just adjust timing based on what the theory says and it'll be fine. That's great as long as nothing changes in the system, which is of course impossible. There's manufacturing tolerances, then there's devices of the same part number will have tolerances as well, and that's before you throw in temperature and aging aspects. So what our system says is we can't know these things, they're impossible. And not only that, we can't actually react in time, no one can. If you're reacting to the signals we showed you before, you're too late, always, which means you're losing the point of soft switching. What our system does is it uses prior knowledge of other switching to predict what to do next. And it's being statistical, and this is where the AI part comes in, we're basically operating with limited information in a noisy environment and still making very clever decisions in a rapid frequency.
I think that's an excellent point to make, James. And one of the things that I was telling people at APEC just a few days ago was that you guys are the first to make a software-oriented power play a primary solution, but you're not going to be the last by a long shot.
Oh no, we hope that we're actually setting up a whole field here. That's what we hope for. And again, the timing is right, because even as I mentioned before, we tried this decades ago. We waited for new switches. We got the new switches, and then we said, "Hang on, what do we do now?" And so we think that we can actually make it work now with all the parts coming together. I think it's perfect timing, especially with the EV boom coming as well.
Well, thanks, James, for taking the time with us. Really, I appreciate it. Oh, and Derek.
Oh.
Sorry about that, Derek.
Good day.
Well.